All right. Good afternoon, everyone, and thank you guys for being here. Welcome to our August installment of ENERCALC Office Hours. Before we get going on the session today, I just want to start with a quick sound check. So, if you direct your attention to the lower right hand corner of the sessions window in your browser, you should see a chat window down there. If you're able to hear me right now, just go ahead and throw a thumbs up emoji in the chat so that we know everybody's getting audio just fine. All right, outstanding. Thank you guys for confirming that. Before we get on to some housekeeping items, we also want to go ahead and do a quick sound check for our primary speaker as well. So Mac is going to unmute. And once again, if you can hear Mac's voice in just a moment, go ahead and give us another thumbs up if you would, please.
Hello, everyone.
All right, fantastic. And also, as a final tech check, you guys should also be able to see the landing page for our virtual office hours slide today. Hopefully, everyone can see their screen share. Let us know if there are any problems with that. Perfect. Okay, now that we have our tech checks out of the way, we are going to go ahead and disable the chat, and then we'll move on to some introductions and get going with today's program. So my name is Seth Roseworm. I'm Senior Structural Engineer and Software Developer here at ENERCALC. Our presenter for monthly ENERCALC Office Hours program is Mac Elterhony. Mac is a Senior Structural Engineer here at ENERCALC, and he kind of splits his time between technical training for ENERCALC customers, working with the ENERCALC engineering team on specs and behavior for our software, and then also helping maintain a presence for ENERCALC at national events. Mac is also a co-founder and managing principal of ELTA Design Group, which is a specialty structural engineering firm based in Oklahoma City. He's been an ENERCALC user for over a decade, so he has a lot of great insight for the needs of our customers. For anyone who's new this month, Office Hours program is meant to provide direct line of communication between us and our users, and it's meant to do several different things. Mainly, we're here to showcase new features and updates from ENERCALC software. We also want to show you guys optimized design workflows. We answer previously submitted questions that people have submitted to officehours@enercalc.com ahead of time. We also do live Q&A and go through hands-on examples. And if there's a question that's too involved or it's going to require deep dive, digging and research, then that's a better fit for our support team. And we can direct that to support@enercalc.com so that the support team can address, investigate your concerns, look under the hood for answers to those deeper questions. As a minor point of order, you'll notice that everyone's microphones are muted just to make sure we don't get any echo or feedback while Mac is presenting our session today. As I mentioned, we do have time for open Q&A at the end of our session. If you want to submit a question for today's Q&A, or if you have technical difficulties of any kind, obviously we have the Q&A dialog in the lower right-hand corner of your sessions window. We'll be taking questions through the Q&A, and I'll be pitching those to Mac for our question and answer at the end. If you do experience any audio or visual problems at any point during the session, you should be able to solve those either by simply refreshing your browser or jumping out of the session and rejoining. With that, I'm going to go ahead and hand it over to Mac, who's going to get going on our program for today.
Hello, everyone. Thank you, Seth, for the great introduction. Without further ado, I would like just to start our session with a brief overview of the agenda for today. So we will be covering ENERCALC latest build, register for office hours to get notified, prepared Q&A. Those are previously submitted questions by our users. And then the theme for our office hours today is steel beam design for biaxial loads. And lastly, we will open the floor for live Q&A. So we have a couple of housekeeping items that we would like to go over. The first thing is, are you using the latest build of ENERCALC? So if you open ENERCALC and look at the very top, you'll be able to see the current build that you are currently on. So we want to make sure that you get notified of all of the new updates to ENERCALC. This way you can take advantage of all the newest features we implement. And we do have these, release these updates monthly. So what I would like for everyone to do is to make sure that they get notified by clicking on the update button, and that will pop up this window. Just make sure you select this option or check mark this option saying automatically check for updates at program startup. This way, every time you open ENERCALC, it will tell you if it detects any new updates. The other item we have today is, are you using are you using the latest build of ENERCALC? For those who are stuck between these builds right here, which is build 2023 8/30, because that's August 30th, all the way until 2024 February 28th. So if you are on that build, the feature to notify you of the availability of new updates does not function properly. If you're affected, then that means you will need to do a one manual update. You can do it either from inside ENERCALC or through the website. Now, if you are on this build, which is 2024 March 4th, the 0304, or newer, then this does not affect you and you're good to go. If this does affect you and you need to do a one-time update, the process is very simple. You can go to the update button again from within ENERCALC, and then click to launch the For Our Users webpage. This will take you to our website, and you can click to download the updater. And once you download it and run it, you'll be good to go and you'll be updated to the latest build. And then, of course, I would always recommend that you go back to the same process that we just talked about and make sure that you allow for ENERCALC to automatically check for updates at program startup. Just for your information, we are currently on build 2024 8.1. This actually was released on August 1st, so seven days ago. So this is the latest and greatest. So make sure you always stay updated to take advantage of all of the various features that we add and the bug fixes and everything. Next, I would like to encourage everyone to register for the office hours program. This way you can get email notifications directly to your email. Typically, the email address we have on file is for the IT department or maybe an admin that manages the office licenses. Sometimes the notifications about educational sessions never actually make it to the engineers, and they stay with the IT person, or maybe they go to the one engineer who bought the license while the other engineers don't really know anything. So that's why I always encourage everyone who is interested in these monthly sessions to register on our website to be notified. You can always unsubscribe if needed, of course, and this is open to everybody, including active subscribers and non-users. So with that being said, you can register by either going to our website, enercalc.com/office hours, or you can just access it directly from our website. If you click on the For Our Users button up here, and then choose the office hours from the drop-down menu. This will take you to the registration page, which is very straightforward and simple. You input your email address, your name, and if you are an active subscriber, we ask you to put your registration number. If you're not a current user of ENERCALC, then you can leave that blank. Then click on the submit button to be included in the email list. And lastly, at the bottom, you can see that we regularly update the information regarding the next office hours session. So you're always in the loop. You can always see here at the bottom, that's which is today. So in the next couple of days, we will update this for the next office hour session. Also, we will have an updated link for you to join. And lastly, you can add it to your calendar. Once you click on it, it'll download a calendar event that then you can just open it with Outlook or Gmail or whatever you use for your email, and it will import directly into your calendar. So at that same page, the enercalc.com/office hours webpage, we also post all of the unedited recordings of the previous office hour sessions. You can find them by scrolling down the page. If you go all the way down, you'll be able to find a bunch of recordings. We also have a title and a date for each recording. So for example, the latest recording we have on our website right now, that is from the July 10th session, and the title of the session is Live and Dynamic Load Linking. You can always go and watch it offline or whenever you would like, instead of just being live. So moving on to the prepared Q&A segment, where we pick a frequently asked question and discuss it. This question, we get this question a lot, this question is, can a user combine calcs from different ENERCALC files? The answer is yes, but I want to give you a little bit of an overview. So one ENERCALC.ec6 file, which is your standard ENERCALC file, one file cannot be opened by multiple users at the same time. This is due to the risk of data loss and data corruption. However, when multiple engineers work on the same project, each engineer is recommended to create their own ENERCALC file. So I can create my own ENERCALC file, and maybe that will house 5 or 6 calculations. And then my coworker will create their own file for the same project, and that will host another 5 or 6 or 7 calculations. Once it's all said and done, once we're ready to wrap it all up, we can combine all these calculations from the various ENERCALC files into one file. We can import them into one master ENERCALC file, and the process is quite simple. So you can import calcs by clicking on the import from other projects button right here. And if you see here to the right, if you click on this question mark button on the right, it will open the user manual, and then the user manual will actually show you a step-by-step guide to how to on how to import calcs. So anyways, but I'm going to walk you through the process. It's really simple. Once you click on the import from other projects button, you can see here on the right-hand side, once you click on the button on the right-hand side, it will get updated, and that will change to display a lot more information. First, you can see a summary of the steps right here. This is a quick summary of the steps on how to import calcs for your quick reference. But also on the right-hand side, you can see this note in orange. There's an important note saying that calcs that have been linked or they have linked loads using load linking. So ENERCALC has the ability to link loads from one steel beam to another, for example. So these loads, this chain, whenever you want, you cannot import the chain into another calculation. So it's very important that you understand that. So there is an important note that's saying that the calcs that have linked loads using the load linking feature will be imported without the linked loads. This is critical, and this might create problems if you try to import loads due to not having those linked loads, or calculations due to not having linked loads. So just be careful how to use this feature. Now you can navigate to select the project that you want to import. So this is very simple. You just click on this button, and then you click whatever project you want. And once you navigate to the project that you want to import calculations from, you can see a whole list of all of the calculations that are actually housed in the project that you selected. You can scroll down and find the calculation that you want to import into your current file. For example, we're going to grab the sample wood beam calc. And once you select the calc, you can click on the copy calc into project button on the top left corner right here. Once you click on this, you can instantly see on the left-hand side that the calculation that you selected appears in green. Now, it's important to note that the importing of the calc is not final yet. It's just telling you that it's there and it's showing it in green. That's indicating that it's not final. It won't be final until you click on finish import. Once you finish import, everything will be good to go, and that's the calculation right here. It's no longer green, and it is in your current file. You can also use the same process to bulk import multiple calculations. So you don't have to do this one calculation at a time. You can highlight as many calculations as you want, and you can just follow the same exact process. You click on the copy calc, and then you click on Finish Import, and they automatically show up into your own current file. Moving on to our next part of the presentation, which is our theme for office hours today, and that is steel beam design for biaxial loads. We get a lot of questions about how to use the ENERCALC to design beams that have biaxial loads. So I wanted to dive into this a little bit. So ENERCALC can design a steel member that is subject to axial loads as well as lateral loads in both directions at the same time. These capabilities are available within the steel column module, for example. This is not a workaround, and that's very important to understand. This is not a workaround. The steel column module is designed to handle and perform these calculations, as evident by the bracing controls provided within the model. So I want to take an example of something that we would do daily, or at least weekly in our projects, and I wanted to just kind of go through the example and show you how to use ENERCALC to design this header. So this is a very common design task, which is a lot of times if you have a large opening, maybe that's very tall, deflection criteria might be a little stringent. So cold form steel might not be the solution, and you will have to install an HSS member that acts as a header, or a hot rolled steel member. So we will walk through this process, or the process of designing this example, and then we will do a live demo to showcase other features that this example did not illustrate. So right here, this is a sketch of what the opening looks like. So to set some of the given information, or some of the things that we know, we want to use a header type that's a tube. So we're trying to use an HSS. The wall width is 8 inches, so we can use a tube that's as wide as 8 inches, as long as it fits into the wall. And then the header span is 17 feet. The bottom of the header is at 27 feet above finished floor. And once you do the wind calculations, we know that we have a lateral load of 555 PLF, and this is ultimate load, 1.0 wind. So lateral load from the window, and then we have dead load, which is gravity load from the weight of the studs and the finished material above. That is 100 PLF. Another thing that we know, that we don't have any axial bracing, so the unbraced length from a buckling perspective for axial bracing is the full length of the member, which is 17 feet, and we don't have any bracing for the compression side of the header. So essentially, for lateral torsional buckling (LU), we will have to use the full length of the member. We don't have it. The unbraced length is the full length of the member, which is 17 feet. So first, we start a new calculation by just following the simple standard process. You click on the Add button, then columns tab, and then you click on the steel column button. And we start, left to right, just the standard process from the general tab, and we work our way throughout the various tabs. So starting at the general tab, we give the calculation a name, and then the first thing you see below that is an input here for overall column height. It has a note that says it's used for bending analysis, not slenderness. So for beam type analysis, you will need the full length to determine the maximal applied load, or the maximal applied moment, for example. So slenderness calculations such as KL over R require you to know the unbraced length. This unbraced length might or might not be the full column height. Hence, we need to know the full column height for bending analysis, while slenderness is controlled separately using a whole different tab. We have multiple options to control it there. So this is not used for slenderness, but it's used for the bending analysis. In our case right now, the header is 17 feet, so we input 17 feet. Next, we need to determine the end fixities. This will also affect the beam type analysis as well as deflection and reactions. So the end conditions for slenderness calculation, for the calculation of KL over R, are determined separately in the slenderness tab. This allows the user to have a great flexibility and a great level of flexibility in their design. So in this case, the header is pin, so no translation, but free to rotate. So that's what this is at the top, bottom, left, right, that's all the same, which is pin, so no moment restraints. Moving on to the bottom portion of the general tab, this has the standard design information such as ASD versus LRFD, your FY modulus of elasticity, and for this case I'm using 46 KSI. You can use whatever you would like to use based on your own specific material. So moving on to the next tab, we would go ahead and select a size to start from. I would like to just go for an 8x4. This way I'm filling the cavity of the wall. I'm taking advantage of it. So it's an 8x4 by quarter, and we want it to be long side horizontal. And for the visual learners, this is the orientation that we want, long side horizontal. Next is the loads tab. You can apply axial loads as well as lateral loads in both directions. In our header example, we do not have any axial loads. We only have gravity and lateral loads, so we will just focus on that. So both of the gravity and the lateral, both are just lateral on the X and lateral on the Y, nothing axial. So we will just focus on this tab. So on the bottom right, you can add, copy, and delete loads. Once you click on the Add Load button, you will be prompted to select a load type from this drop-down menu. So you can apply fully uniform load, you can apply partially uniform, point loads, and partially uniform loads, point loads, and concentrated moments. So I'm going to start by applying a fully uniformed distributed load to represent the gravity loads from the wall assembly above the header. So I typically, the first thing I do is just put a nice description of the load that I'm putting. And in this case, I'm going to put gravity load for the self-weight of framing above header. The value of this load, as we remember, it's 100 PLF. So that's equal to 0.1 kip per foot. And it is applied as dead load. Then you need to select the direction of the load. So is it parallel to the X or is it parallel to the Y axis? If you click on the 2D tab within ENERCALC, you will be able to see a 2D representation of the cross section. Also, if you click on the 3D tab within ENERCALC, you will be able to see a dynamic 3D representation of the whole header. I personally use the 3D representation, and what I do is that I just manipulate it and orient it in the way that makes sense to me and allow it to display the axes so I can see the direction of the loading. Now that I have the tube oriented the way that I want it, which is this right here, the long side horizontal, then I can see what the x-axis is and what the y-axis is. So this way I can apply my loads in, very easily. I can visually see how to apply my loads. And of course, we want to apply the gravity load for our header example in the weak axis. So it makes sense. That's the x direction of the HSS. Next, we repeat the same process by clicking on the Add Load button and apply the uniform load to represent the lateral load. That's the load from the head of the window that's acting on the HSS. So again, I add just a description. So this way, whoever is reviewing this in the future can easily know what loads, where the loads are coming from or what the loads are describing. And we go ahead and apply the 555 pound per foot or the 0.555 kip per foot loads, uniform load that we have on the beam, and that is wind load. So we put it in the right category, so this way the load combinations will be performed properly. And again, from the 3D tab and the 3D representation of this beam, it's very clear that the y direction is the strong axis, so we're applying the loads that way. So once you apply the loads, this is actually what the 3D visual looks like from inside ENERCALC. Once you apply the 0.1 right here and the 0.56 kip per foot, that's exactly what they look like. Again, this is just a quick sanity check for you to see how your loads are applied, if they're applied in the right direction and in the right orientation. It is also worth noting that all of the loads that you apply on a member are summarized in this table right here. So you can see this is the load that we applied, that's the dead load, and then that's the other one that has the wind load. So this, again, allows user to be able to see all of the loads that are applied and cycle through these loads very easily. Now, if you're ever confused about the sign convention that ENERCALC uses, and just kind of wanted to quickly reorient yourself, you can simply click on the load reference guide button on the top right corner, this button right here. And when you click on that, you will get this pop-up window that shows the sign convention in great details. This is the sign convention that we use for the for this module. So the next tab is the slenderness tab. In this tab, you can assign bracing condition for axial buckling, which is also known as Euler buckling. You have the option to specify bracing conditions about the x-axis separately from your bracing conditions in the y-axis. So in this tab right here, once you kind of pick your X and your Y, or you have controls for the X and for the Y, so the user will have, full control over bracing. You can pick the member is fully braced, or you can select a K factor based on the standard predefined conditions, such as, pin or fixed pin and so forth. You can input your own K factor if you don't want to use the standard configurations. And lastly, you can calculate the K factor using the adjacent members, and ENERCALC will help you perform those calculations. You can directly define the unbraced length, LU. So you can just choose if you click on this one right here, you can specifically choose what you want the unbraced length to be. If you want it to be 10 feet, if you want it to be 5 feet, if you want to do that. Also, you can select the use overall column height, this one right here, this option. So you can select, the overall column height option, and when you select it, the program will then multiply the K factor that you picked by the overall column height to determine the unbraced length. This LU, or this unbraced length, will be used to determine the axial capacity of the member by using it, of course, in determining the slenderness ratio, the KL over R, for each direction. So if you use this option right here, and then whatever you used in terms of, whatever predefined condition for your K, then it will just multiply them together. In this case, it's using the overall column height, and it's multiplying it by KX, which we're using in this case to be a pin. And we can assign the K values for both buckling directions. So for our header example, we assume that the header to be pin, hence a K factor of 1 is applicable in both directions. Keep in mind, the header we're designing does not have any axial loads applied to it. So this calculation is not going to control the design at all, because the applied axial load is 0. However, had we had any axial loads applied to the header, then ENERCALC is prepared to perform the proper calculations. A lot of times, maybe you'll have a little brace that's on top of this header. This header is part of a bracing system. Maybe there is a little bit of a shear wall, like a pony wall on top of it. So there are multiple avenues where you could get a header that's also acting as that's also receiving some sort of axial loads. But in our case right now, it's not receiving any axial loads. We move on now to the next tab. This is the beam stability tab. In this tab, we're prompted to assign an unbraced length for the calculation of the flexure about the XX axis. This is critical for lateral torsional buckling. So if we have a normal column that's subject to only axial loads, then this tab does not really affect the capacity of the column because the column is only subjected to axial loads. Only slenderness would matter in that case. However, when a column has lateral loads, then we will see a beam-like behavior in terms of flexure. Hence, the equations for typical beam bending design actually apply. And ENERCALC allows the users to control beam bracing for flexure calculations separately from the slenderness bracing to ensure that the users have great flexibility to reflect the bracing conditions that they want. So in our header example, it is important to determine the unbraced length that controls the flexure design. And in this header case, of course, the full length is considered unbraced length and will have to be used fully. So therefore, we're using 17 feet. Just to take the discussion a little bit further, if there were joists framing to the top of this beam, so if we have joists framing to the top of the header, and let's say these joists are spaced at 5 feet on center, I would probably, and if they're bracing the compression side of this header, then there's nothing that prevents me from taking advantage of this. As a matter of fact, I will take advantage of this and use the unbraced length for flexure, which is the beam stability, as 5 feet instead of 17 feet. Again, this is a tube, so it's not a big deal. But if this was a W-shaped member, for example, this will definitely have a significant impact on the bending capacity of the beam. Lastly, as usual, the last tab is the load combinations tab, and you can select to run whatever load combinations you want. For the sake of this example, we're just using standard IBC 2018 load combinations, and we're just having everything run normally, all of the combinations. So this concludes all of the design data that we need to input. And at this point, we are ready to evaluate the results. So under the Calculations tab, you can see a summary of the results. You can see applied loads as well as allowable capacities. You can see the applied loads right here, and then the allowable capacities. And we're using ASD design here, so you can see the ASD allowable capacities. You can clearly see that we have axial load 0. It's still calculated the capacity, but the applied axial load is 0. However, we do have mx and my, so we do have these loads applied, in the biaxial direction. You can clearly see that again, there's no axial load, and that's why it's 0. And at the very top right here, the results that are reported, or the controlling result that's reported, it's the combined result, because you have multiple loads coming from different directions. So the combined value is here 0.5859, which is of course less than 1. Hence, the design is safe. Moving on to the next portion here, you can see the maximum lateral reactions along the X and the Y directions. The results as are displayed, for both sides of the member. So the top and the bottom, if it's a column, left to right for a beam. But you can see the maximum reactions in both of these directions, the X and Y. And of course, the maximum deflections at each end of the beam. The maximum deflections at each direction, which is the X and the Y, and it tells you also the location of where the max deflection occurs, and the load combination that produced the deflection. At the bottom here, this is a quick piece of information. You can find your KL over R for the X direction and the Y direction. That's just for again, for a quick glance, if you really want that number quickly to maybe run your own hand calc or do a quick quick verification. Another useful output is found under the Diagrams tab. One of the things that I like about the diagrams is that again, we like most engineers, most structural engineers like to see what the moment diagram looks like, what the shear diagram looks like. That's kind of our sanity check. We have an expectation of what it's supposed to look like, and we want to be able to see that the final diagram actually reflects what our expectations are, and if it's not, then we want to investigate further. But in this case, for example, you can click on the moment here, and you can select the axis that you want to see the moment for. So this is the X and this is the Y. So you can see all of that information, all that information displayed for you to evaluate the results. So in conclusion, the steel column module is designed and fully capable of performing calculations on a steel member that is loaded in all three directions, X, Y, and axially. Granular bracing controls allow the user to determine bracing conditions for Euler buckling, just axial loads, as well as bracing of compression side for lateral torsional buckling, which is typical beam behavior. So with that being said, I'm ready to jump over to do a quick live demo because I want to show a couple of things that are critical that this header example did not cover. So this is the header example that I was talking about right here, and this is the 2D tap. You can see the loading along the Y, loading along the X, and of course you can see here the cross section. All of this information is normal information we just went over. This is the part that I want to show you, give you a little bit of information about. This is the axial loads tab. Within the axial loads tab, you can add a load. And for example, maybe I want to add 2 kips. And you can see that the load is applied right here. There you go. Along the z-axis, this is the load that's already applied right here. And what you can do is that you can of course add the column self weight if you want, but since assuming this is a header that's taken axial load, so the self weight is not gonna be applied axially. But what I want to show here, and that's very critical, you can have a point load that's applied to the top of the column. You can have it applied maybe at 5 feet, a very specific location. But more importantly, what I want to show you is this right here. This shows you the eccentricity. So you can apply the column concentric, the loads concentric on top of the column, or most of the time we don't have that. A lot of times you have a beam that frames into a column, for example, or maybe in the header example, if we have a shear wall that's on top of it, then the load will be really applied to the outside face or the top face of the beam. So that's why it's critical to apply these loads with the proper eccentricity. So for example, I want to apply it maybe 2 inches measured from the edge of column. So you can see right here how this load changed. Let me do this. Let me do 0. If you want the load applied directly at the face of the column, then it's right here. If you want to apply it at the center of the column, you can see that this is dynamically changing to show you that it's applied at the center. If you want it to be applied at 3 inches from the face of the column, then you can just click right here and you apply it there. And if this, for some reason, has also a Y eccentricity, be 1 inch from the center, then it's like that. If you do it from the face of the column, it'll push you all the way up there. So you have a little bit of extra controls. ENERCALC will know to take the axial components of this, to work it with, to apply it to the column axial capacity, and then it knows that there is now moment that's being induced, and it understands if this moment on the column is being induced in the x-axis alone or in the y-axis alone, or there is a portion that's going in both directions, and it will figure out what that component is and applies it
and applies it accordingly. So that's kind of the part that I wanted to show. And again, this is a quick load reference guide. This will show you how all of the loads, what we assume as a positive direction and negative direction, just to give you a better idea. And you can add, a bunch of axial loads right here. And again, this is the lateral loads that we just talked about. You can choose whatever you want, and you can apply it parallel to whichever axes you would like. The slenderness, just to go through these, the first option, obviously saying it's fully braced. Second option is determining your own unbraced length. So this way it doesn't do any calculations. It doesn't consider K, it doesn't do anything. It takes it. It takes your unbraced length, your LU directly from there. Or this is the option that we elected to do, which is use the overall column height and just multiply it by the appropriate K factor based on what we select. So if I selected this, for example, then it knows to switch it to 0.8 instead of 1. So based on what we use here. Input K factor. This is if you want to put a specific K factor that you've already separately calculated. That's not, one of these standard. Maybe you want to put a 0.85, for example. You can just come into this tab and just say K is 0.85, and it will perform the calculation properly. And then lastly here, this is the portion that helps you compute the K factors based on the adjacent members. You can do all kinds of stuff here, but this would help you quite a bit in running the calculation. Most of the time, this is sufficient for what we do, for what most engineers do anyways, especially on single-story and two-story buildings. And again, this is the beam stability, and those are load combinations. So this is also another thing that a lot of people are not aware of. This button right here is useful because a lot of times you can just come right here and you can see the various available materials. So this is a quick reference. Instead of having to go and look it up, you can always, if you know what material you want to use, you can reference this quickly and pick whatever material you want from here. So this pretty much covers the various controls that we have. And let me see here. The various controls that we have for the steel column module. And I think, yeah, we're ready to open this for some Q&A. That would conclude my my portion of the presentation, and we're ready for any questions, and Seth can take it from here.
All right, fantastic. So just as a reminder for anybody who has questions, refer to the lower right-hand corner of your sessions interface, and you'll see the Q&A tray, and you'll be able to go ahead and submit your questions there. We'll just go ahead and start working our way through these. So question from Kamal, is load linking available for wood structures, for example, LVLs supported by LVLs? Mac, you want to go ahead and take that while I'm going down through these, or I can? It's up to you.
Where's the question? Did it pop up?
Sorry. Right there.
Okay. Is load linking available for wood structures? So load linking right now is available only for steel beams. However, and let me actually share my screen here. Okay. Cancel out of this. So it is currently available in steel beams, but we are working on implementing it in pretty much all of our modules. The thing is that, and this is kind of what I want to show you, we are, we can't implement everything at once. So, but we like to hear what our users have to say. And if you see right here, the ability to link reactions from columns or even from other calculations or wood or all of that stuff, it's still being introduced. So what we want people to do is that just jump on this load linking survey, and this would allow us, if you click on start, this would allow us to know what people want to see first in terms of development. And, the more requests we get, then that particular module will get all of the we'll get the priority. So again, right now we do not support the we do not support load linking in wood beams. However, that is something that we're planning on doing, and we're just going to see what people want us to implement first, right after, since we're done here with the steel beam implementation.
All right, perfect. All right, going down the list here. A question from Jonathan. Will ENERCALC allow beam bracing in both XX and YY directions for biaxial loading in the future? So this is a good question. It's actually, and Mac, feel free to chime in on your thoughts on this question. As far as I'm aware, it's not all that common to run into a steel section that had, or other types of sections for that matter, that are subject to lateral torsional instability about two axes simultaneously. So the primary focus of the lateral torsional bracing controls in the example that Mac highlighted is primarily focused on the one axis that would undergo lateral torsional instability. For wide flanges, that's typically the strong axis, because if you're lying in weak axis, there is no instability. There are some cases with HSS sections, if you get really extreme aspect ratios, you can get lateral torsional with an HSS, but again, that would only affect the one axis with the extreme aspect ratio. It would not affect both axes simultaneously. Mac, do you want to chime in with thoughts on that?
That's absolutely correct. You're not going to
question
have
that's
it
on screen right now.
Yeah. Can you see? We go to beam stability. Yeah, this is exactly what it's for. So this says flexure about the XX axis, which is the strong axis. That's where lateral torsional buckling is going to control. Even if you have again an HSS, if it ever controls in an HSS, it's still going to be in the primary direction or in the strong axis. It's not, that's the slender part. It's not going to be flat wise. It's not going to control. That's why it wouldn't serve much purpose to have the ability to do that in the other direction, because it's not going to control. That's what I'm trying to say.
Perfect. Okay. A question from Joe. It looks like you have brick veneer in your sketch for the example. What about torsion? Let me go and put that.
Yeah. So let me get you back here. For the purpose of our example, I was actually ignoring the torsion from the brick veneer. I was even ignoring the weight, of the brick veneer, because I'm only putting 100 PLF. So in this particular case, or the steel column module will handle biaxial bending and axial loads, but it will not handle torsion. That's not something that's capable of doing.
Perfect. Okay, question from Senchit. Can you also show how you made the tube to be turned long leg horizontal? So correct me if I'm wrong, but since we're using a biaxial column behavior to synthesize this calculation, that has to do with load directionality, correct?
Well, actually what I did, so the default of this is going to look vertical. And as far as the display, because I want to answer two parts. I want to answer the display part and I want to answer the load part. But the display part, I mean, the column is going to start like this. You can flip it and do it however you want to help you kind of get where you need to go. So for example, I'm reorienting this to look like something that I'm familiar with. And then now I can see, the X direction here, the Y direction here. Then now I have kind of my bearing a little bit. I understand what's happening. I can come and apply right here. I can apply the load. And when it says the load is applied parallel to the X, I know it's applied in the weak axis. If it's parallel to the Y, then I know it's applied in the strong axis. And that makes sense because we're applying the 500 pounds, PLF in this, along the strong axis while applying the 100 PLF only in the weak axis. Now, more importantly, this right here in the 2D tab, this is very clear on what the strong axis is and what the weak axis is. So the X is the weak, or the direction of the X, that's the weak axis, and the direction of the Y, that's the strong axis. So I can simply, again, I know that how the load is applied. So for example, the gravity is going to be in the weak axis of the of the HSS. Hence, it's going to be parallel to the X. What I did that's a little bit different, that helps, I think it helps everybody, is that I come here in the 3D and reorient it like this. So I'm always looking at it. Let me bring it here for you. You can see the x-axis. Yeah. So I'm always looking at it in a way that's the right orientation for me. I see the X, I see the Y, and I apply the load as I go. So it's not like we're telling it here anything that we're not telling it to flip anything. Everything is done the same exact way. I'm just flipping or manipulating a little bit the 3D rendering, and then using that in helping me figure out how I need to apply my loads.
Perfect.
The reason that here's what I'm alluding to. In the steel beam, if you just go to a regular steel beam calculation, we have a specific option in there that says, that the beam spans in the minor axis. This is this right here. So this one already flips the beam for you. However, in the column module, we don't have that. We just keep it, because, if you're trying to flip the beam and then now you have to deal with flipping the axes, it becomes too much. So what you do in the columns, we don't have an option to tell you to flip or rotate the member. It's just you take it, you manipulate it however you see fit, and you apply your loads based on the manipulation you chose.
Cool. All right. Next question. Go ahead and put this one up. It's a little bit long, but I'll read it out for you. Under load combinations, there's an option to add SDS and a row value, rho or omega. Does that make any difference to the calculation? For example, a cantilever column, etc. I did use rho, but it doesn't seem to make any difference in the calc. So the rho or omega factor that you can apply in your load combinations is a multiplier with the existing seismic factor that's in the first factor column. So if you add something in there, it's multiplicative with whatever you have for the factor that's already been applied. So if your seismic is the controlling case and you apply a rho or omega, then you'll definitely see a response in your resulting unity check, your deflections, your behavior of the column. It could be in your case that seismic was actually not the controlling case, but definitely you will see the effect of that rho or omega factor, because if in Mac's example right here, if he goes ahead and fills that in, you'll see it populate in the row column on the far right hand side. You'll see that pop up, and so what will be applied in your actual combinations would be multiplicative between the factor column and the row column. Like the building code specifies. So in a case where you have lateral behavior or you have axial behavior that's strongly governed by those seismic combinations, then you would probably see that in play. But feel free to reach out to the support team if you have more questions about that, for sure.
I saw a question here that I want to just jump to real quick. Let me actually bring this one up. Okay, not this one. I think I grabbed the wrong one. It's this one here. The unbrace. So this one right here, it says unbraced column height appear to be 27-foot mark. Y is 17 feet used in the calc. I just want to make sure that we're on the same page. I'm not trying to design the column. I'm designing this header right here. So I'm not messing with the column at all. So the header span is 27. The header span is 17 feet, and that's why we're using 17 feet for this header design. We're just designing this header within the steel column module, because the steel column module is designed to handle, axial load in addition to biaxial bending. But yeah, 17 is for the header. We're not designing the column at all.
Perfect. All right, question from Silas. Does automatic member selection work with the beam column design? So effectively, the beam column design that he's doing here is just using the traditional beam module, and any process that you're doing that uses standardized library-based design, whether that's standardized AISC sections or standardized NDS sections for beams, columns, etc., you should be able to see that in action just like you can in any other module. Definitely, if you're having any difficulty with that, reach out to the support team and they can drill down and see. You'll want to make sure you're on the latest build. And if you're seeing a bug or a unexpected behavior, yeah, definitely reach out to support@enercalc.com to get more
I just
detail
kind of
on
want
that.
to, sorry. Yes, and Seth, I just want to show this here real quick, at least to give people an idea, because a lot of people don't know about it, that you have the automatic member selection, and you can do a variety of things. For example, if I want to use a rectangular HSS, and I can run a depth limit up to this much. I can run a depth class. I can do a variety of things. I can even limit it by a maximum stress ratio that I'm okay with, and then you just kind of start, click design, and it just goes through the various options available, and it goes from there. So
I want to go ahead and
I'm
hit
not-
one more real quick, Mac, while we still have a little time before the end of the
Okay.
hour.
Yeah, go ahead.
Sorry, just to hit another question from Joe. Do you have to manually change dead load when changing the beam size? So, and what he's making reference to obviously is in our traditional beam module where you have a fixed orientation for that beam, you can accommodate the dead load associated with self weight automatically. In this case, since we're using an arbitrary orientation and basically orienting manually with our load directionality, then he's correct in saying we would need to manually
Add that.
adjust the external applied load to consider the fact
Correct.
that the section size has changed.
Absolutely, yes. Absolutely, yes. So you can, within your dead load, you can account for, you can apply that externally right here as an additional load, or you can add it to your dead load and put it in the right orientation you need it to be. And in this case, would be along the x-axis.
Perfect.
Yeah.
All right. Well, I think that actually clears all of our questions. I kind of want to wrap up by reminding everybody a lot of the questions that we do cover during office hours are questions that are sent by email ahead of time to our office hours at enercalc.com. And Mac goes through those and prepares training content based on what people are interested, what people want to see. And so definitely keep those going. Make sure that those keep coming so we know what you guys are interested in. As we wrap up, I will go ahead and toss it back to Mac to give us an update on office hours for next month. As a reminder, if you're not subscribed, make sure you stop by the office hours page on our website, enercalc.com/office hours. That's where you can register so we can reach you directly. Otherwise, mass emails about topics and timing for office hours will sometimes go to, system admins or purchasing offices, and then it won't reach you guys who are the end users. So Mac, I'll go ahead and toss it to you to wrap us up with any final thoughts or detail you want to share about next month's session.
Yes, next month's session is going to be Wednesday, September 11th. And again, keep on sending me your questions and suggestions. And we still haven't decided what next month's theme is. So send me messages and we'll try to cater something to your liking. Thank you very much.
All right. Perfect. Thanks, Mac. Thank you all very much for being here. And with that, we will go ahead and wrap it up, and we'll look forward to seeing you guys next month.